I just want to say that this is the 24th webinar that we've done for the Rigaku Life Science webinar series over the last 2.5 years. So for those of you who have come to past ones, we invite you to come and see future ones as they develop. So without further ado, I'm going to hand this over to Jim and make him a presenter here. And hope each of you enjoy the webinar today. Jim?
Thanks. So I am now the presenter, but I need a tool that says show my desktop, I think. Let's see. You are sharing your desktop. Can you see me?
I see it. I do. I see your desktop.
Okay, and this is my first slide, so thanks everybody. I guess I lost my, that's the whole PowerPoint there, right? It's
correct.
Filling the whole space. Great. Okay,
sure.
Thanks a lot, Angela, and thanks everybody for stopping by to watch this webinar. It's an unusual one for me because I'm talking about something that I use, but I actually haven't really contributed to the software for this. And I do have, as we go along, I'll try to show 3 examples. And this is also should be useful to all of you past today, because if you have to teach somebody in your group or your lab how to use HKL to process data or to do phasing and display models, then you can just say, well, go to the Rigaku webinar and watch this, and that will save you a lot of grief, because they can watch this first, and then they can ask you questions, and you can explain things to them. So HKL3000 is a package written by Vladek Miner, Marcin, Zbyszek, and others. And I want to give credit where credit is due, and throughout this talk I will have the, if I can figure this out, I will have the references shown here so that people who are watching this later can go back and look up the references and read them. And this was published a few years ago, and there are many other packages that also do structure determination from the FOBS to the final model. And I think many of you know about Phoenix, the Phoenix package with the auto build and the auto solve. There's HKL to map. You can use the CCP4 package, and there's some others out there. Today I'll just concentrate on HKL3000, which we're using in our lab. To have this, I'll probably run over a little bit, so I want to get in some acknowledgments. I want to thank my colleague Joe Ferrar for sponsoring all of this, Angela Criswell for supporting this and doing the webinars, Vijaya Madakasira, she actually grew the crystals that you're going to see me work with, and Mark Prestbridge contributed to the strategy that I use, and also some of the space group determination stuff, which I'm not going to talk about today. And then at HKL Research, Vladek Miner and Marcin are key players that I interact with on this. And what you'll see is that the whole crystallographic community and other people wrote a lot of great software that is included in HKL3000. So to go into it, if this is the first display window that you get, and what you see here is, and I'll run this hopefully in about 20 minutes. We'll go through 3 examples. This is the main window of HKL3000, and there's a series of tabs across here: project, data, index, strategy, integrate, scale, and structure. And I put them up and down here in the left-hand side so that you can see them better. On the project panel, or dialog here, you would enter the amino acid sequence and so on. And we'll go through this to allow the program to have some basis for doing the chain tracing and so on. The data tab is similar to what many of you are used to with HKL2000, where you will enter in the directory and names of images or perhaps already processed reflections and so on. And there's some editing that you can do with this. Also, at the top, there's a site configuration. It would be up here. And this is used to set the beam position and a few other things. But mostly, if you're coming from a beam line, or maybe you have several instruments in your lab with different beam positions, you can enter the beam position up here, and that's important. Also, part of this is a way of displaying images, and there's the XDisplayF program, written originally by Vladek, and we'll talk about that in a little bit, but you can look at the beam position, zoom in, set the integration box, check something called the profile fitting radius, and also mask out the blind region. There is a indexing step. Oh, I just solved another structure. Let me go back to this. There is an indexing step here, and we'll go about that in detail. This panel or tab here will allow you to predict where all, determine the space group or determine the unit cell, be able to predict spots, and set some things such as the spot size and the box size that you're using. I'm going to skip over the strategy tab. We don't have time to go into that today. And I'll give a few tips here on these items that I just talked about. So this is in fact the index tab, and many of you know that you'll find spots, you'll do something called indexing where you try to match the spots to a Bravais lattice type, whether it's primitive, triclinic, all the way up to primitive cubic. You can use this to look at your spots with the display program and so on. This display program, this is for crystal, I think, of Thalmatin, yes. And I'll pause now to show you how I get to this stage with a lysozyme crystal here. So one of the things, let's jump out here. And Angela, you're going to have to tell me if this is showing up, my whole desktop. Is that right?
It is showing up.
Okay, thank you. So I have several windows open here for all my examples. Here is my lysozyme, so I would just type in HKL3000. This is actually from the lab here. It's on an R-axis HTC. Bring that in. The images are in this directory, so I press this double arrow. Can load the data set. There are about 173 images. And I know I talked to some of you yesterday or by email. I said I might use some of your images. These are images collected here, and I'm not using your images today. So this is standard HKL3000 for some of you. And I would do a peak search. Here is the spots it found. Then I do index. Typically, you could pick primitive triclinic to start with, and I do refinement with just a few parameters to convergence. Then I do fit all, and I do refinement until everything has stopped shifting to convergence. And I guess I should turn on the mosaicity. And then I come over to this window here, and if I click on Zoom Window, and the thing to note here is you click the middle mouse button to move around in the display. And I zoom in, and if I click on integration box, it shows me an integration box here. I will explain these graphics here in a moment. I'm looking at this, and I wanted my box size to be bigger, and I would click on that. That actually looks pretty good to me. Close this. Here I am. One of the things is these are not all the predicted spots. These are the spots above 5 sigma, I believe here. If I turn on the profile fitting radius or I turn it off, I get the predictions. So I want to process out to the corner. Spot size, box size is okay. I want to maybe check the Bravais lattice type. Since it's a tetragonal lysozyme, I kind of know what the story is there. Finally, there is a, just a moment, bring this up. And I have a blind region that's used to mask out the shadow of the beam stop. To define the blind region, click 2 times. So this is for a circle. This is for a quadrilateral. And I'm doing this once again so that you can pass this on to your colleagues and they can see how to run the program. Apply current, close this, refine, refine. So I have convergence. Everything's gone to 0 here. Predictions look good. It may be, you should know this. If there are no strong spots within this or no yellow spots within this circle of this profile fitting radius, it will not integrate any of those spots because it can't do profile fitting there. A trick here might be to say use lower sigma cutoff. Another trick, a lower sigma cutoff in the reference profile or reflections that go in the reference profile. Another trick might be to increase your profile fitting radius and watch what happens here. Now that I have a larger profile fitting radius, I do have some yellow predictions or yellow spots in that circle. So I'm just about ready to integrate, and I can go to the Integrate tab and press Integrate, or I could have pressed it before. So now this is off and running, and I'm integrating what's going to be 173 images of lysozyme. So let's go back here and talk about what I just did. All right, so I set the spot size to encompass all the spot pixels, the pixels in the Bragg reflection. If it's too big, you'll have spot overlap, and I'll show an example of that in a moment. If it's too small, you'll exclude some of the intense pixel values that actually need to go into your integrated intensity. At the same time, working with the spot size, you want to do something called box size, and it has to be about 3 by 3 times the size of the spot. If it's too big, you'll have background calculated from pixels that are not near your spot, not near the Bragg reflection. If it's too small, you won't have enough pixels in the background. And this is an explanation of that. So here's a capture of a zoom window, and there's a few Bragg predicted spots here with yellow circles around them. And what you'll see here is that I have a spot radius set, and that is given by this orange circle. So it essentially, and also by these white lines in the graphic. So that's the pixels that are going to be used in the integration of this spot. And the color scheme, this orange, is, I was just thinking of Halloween. It's kind of like a pumpkin, I guess, at least here in America. So the spot radius, that's what you're setting, a radius to completely encapsulate the Bragg reflection. There's also a background radius, which is kind of a light green here. This background radius is set so that anything outside that background radius to the edge of the box will be included as a background pixel, a pixel used in the background calculation. So this is giving me my spot box size for the spot here. Once again, the integrated intensity is going to come from the pixels within the spot radius that will then be profile fitted to the reference profiles. The other thing to note here is that once you have this sort of purplish background, I've made it big enough so that I could put 9 of these spots in here. It doesn't, in my opinion, it doesn't have to be much bigger. And notice also that I'm not going further than halfway into the, or closer than the center of the neighboring spots here. So I have enough background here to estimate the background while not going to the neighbor. So another way of looking at this is you also have to remember that neighboring spots that intrude within this purple box at least are not anything outside of the green circles here, anything outside the background radius, and within the purple box is where the background is estimated from. And I believe that HKL or Denso makes a least squares fit to a plane of the background around here. So it's a very local background. If this box was huge, you would be estimating the background for this Bragg reflection by including spots around over here, and I don't think you want to do that. So this is an explanation of spot radius, background radius, and box size, and you have to get that down to understand how to use this program. Now, I've already clicked Integrate in the other window here, but you can generally, it will plot the mosaicity as it goes along. You'll see the refinement here as it goes along. The positional and partiality reduced chi-squared should be close to 1, which is saying that whatever you told the program is the expected error, it agrees, your data agrees with it. The reality is if these shifts are all 0, you're not going to change these numbers here at all. If you see things moving around in these plots here, then there may be something pathologically wrong with your goniometer, or your crystal is moving, and so on. So after you've integrated, you'll do scaling, and we'll talk about scaling in a little bit more detail here. There is this tab for scaling. It has the results shown at the top and some controls shown at the bottom. My recommendation is always turn on absorption correction, always turn on anomalous, because there's always an anomalous signal, whether you, doesn't matter what wavelength you're at. And always turn on the post-refinement, where you will have a small slippage and imperfect goniostat. Maybe someone can explain to me where you may have to do something different, but I haven't seen that going. And you would press this button, Scale Sets. So, of course, you want to suggest the space group hypothesis first. So then do these 3 things: absorption correction, anomalous, small slippage, and look at the results, and you may make some other adjustments then. So let's go to back to my display here. I finished integrating the data set, which is a lysozyme collected here. You can see that the cell parameters didn't change much, the crystal orientation angles didn't change much, the mosaicity didn't change much, and the crystal detector distance didn't change much. So this is an okay crystal. Obviously, you know, it's a talk, so I'm using pretty good data for most of this. If I go to scaling, I won't show you how I know the space group, but I do know it's P4 sub 3, 2 sub 1, 2. I said turn on absorption correction, turn on anomalous, turn on small slippage, press scale. Let's see what happens. And so it's scaling away here. There's about 100,000 observations, and let's look at the plots here. So the R merge is, well, it's about 2.6% with taking into account that you've separated I pluses and I minuses from each other. So we see that the scale factors vary more or less smoothly, but they're restrained. That's fine. The completeness is good out to about this resolution, which is about 1.6-ish, it looks like. The reduced chi-squared for the images is, it looks like here it's about 0.5. So our sigmas are much, much higher than they need to be. The R factor is about the 2.6%. Here in this panel are the red and green, and the blue and yellow are telling us something about the anomalous signal here. So the blue and yellow are the reduced chi-squared for reflections in these batches, and I'll give an equation for what the reduced chi-squared is in a moment so you can completely understand that. The yellow is when I plus and I minus are combined. So you expect the data, the chi-squared, to be higher if there's an anomalous signal. If there is, the blue is when I plus and I minus are kept separate. All reflections belonging to reflection off of, say, one side of the reference planes in the crystal, I pluses are combined together. The are treated together, I guess. Combined is not the right word. And all the I minuses by reflection off the opposite side of the plane are treated together. If you have only normally distributed random errors, this line should be close to 1, which would be right here. The red and green lines are the crystallographic R factor, or the R merge in this case, with red having I plus and I minus kept separate, and green when you combine I plus and I minus, or treat them as equivalent. So when Frito's law holds, it's as if you're using the green and the yellow lines. If Frito's law is disobeyed, it's, while you're keeping things separate, I plus and I minus separate, you're using the red and the blue. So if I look at this, I need to adjust my sigmas so that this blue line goes up to 1. And adjusting your sigmas is the same as adjusting the error model. I generally, in this button, will set the error model to be equal to about our merge of the data, which I think was 2.6. And this error scale factor, I can reduce it. And I'm just going to take a wild guess here and reduce that, which will make those numbers go up. The other thing I like to do, and some of you like to do as well, is to maybe set the resolution cutoffs. If I look at the low resolution completeness, the shadow of the beam stop probably begins around 22 angstrom, and then the cutoff here, I said 1.6. Let's just put it at 1.6 and see what happens. So, to review, I came in with the data. I set absorption correction, anomalous, small slippage. I pressed the button. Then I looked at the results, and now I'm sort of looking at trying to get the estimated standard uncertainties, or the sigmas, more or less correct, so that the spread from the R merge matches the standard deviations estimated from integration from the Poisson counting statistics. So if you look here, it's done scaling. I don't think the R merge has changed any, because we haven't changed the number of reflections we've used or anything going into the equation. This green, or the red dots here, the chi-squared is a little bit too high. And here on the blue line, it's a little bit too high. So if I bring this back up to 1, use rejects, press the button, and I think this is probably going to be close to what I need to do. And I did this by trial and error. If you use auto corrections, this can do some of this stuff automatically. There's a couple of things I did not do, just for your reference. I did not go into adjust error model and change all of the shells separately. I'm using the R merge here for all of the shells. And if you look here, this is close enough to 1 for the blue line, and there's a little bit of an anomalous signal here with the yellow line. And this is a little bit too low. So what can I do here? One is too high, and I think well, maybe I did it wrong. Let's try, did I go the wrong way? Let's try 0.8. So the interface is quick enough and the program is quick enough that you can do a lot of stuff by trial and error. So basically, I just made a hypothesis that if I make this by 0.8, that this will be closer to 1. So I went the wrong way, and I will change this to 0.95 and run it again. And I think I'm already playing around with this too much for this seminar. I think we'll be fine with this. And there's my answer. Everything looks good, about an R merge of 2.6%, and so on. And obviously, the completeness really falls off, not at 1.6 angstroms resolution, but closer to 1.7 and so on. But here's the output SCA file that I can use in subsequent crystallographic endeavors, including the structure determination stuff here in a moment. Okay, so back to the PowerPoint presentation. And I think if I click here, it'll come forward. Right. So set the space group, turn on absorption correction, turn on anomalous small slippage. So when you click on that anomalous button, a couple of things happen. The output file, the output SCA file, it gets columns of I plus and I minus. If you don't have that option on, I plus and I minus reflections are merged or averaged together, and you will not be able to do the subsequent SAD phasing steps because the data will have obliterated the anomalous signal for you. The other thing is that R merge anomalous is actually this equation where you compare the reflections that are designated plus with the average for that group of plus reflections. And you compare the reflections designated minus, here the HKL H minus, with the average, that's H minus. So this value is always lower than R merge, okay, where you have these things together. And I'll just call this R merge a nom. It's always lower. I did talk about adjusting the reduced chi-squared. I did reject the outliers by using the rejection. And if there's images to reject, you should do that. I discussed a few of the plots. And one thing I want to talk about separate here now is that we've written a SCA to Dirac program so that you can compute R measured, I over sigma I, and table 1. So if I pop out here, and let's see, where am I at? CBGLS. So in this directory, I have my results, and I've written a little script that I will edit and show you what I mean by the SCA to Dirac to calculate your table 1. So it turns out you can, when you're clicking these buttons for scaling, you're actually running the program ScalePack. The interface produces a scale.in file, which I will include here, scl.in, and these are the commands to go into the script. And I'm going to make a no merge output file here. And this may be confusing to you, but you'll see in a moment what's happening. And I'm putting it in this webinar so that it's here for posterity and future training. So I'm adding the command no merge original index. And other than that, nothing is really changing. And I'm just deleting the comments I had in that. So if I run this script, it actually will do the scaling again. But the output file will now have all the observations that have not been averaged together into unique data. So the output file coming from the interface, the earlier run, is right here, and it has the unique data only. The no merge output.sca has all of the individual measurements here coming out of the program. I can then run on that file SCA to Dirac, and if you look at that, it will now convert all of this stuff to the D-Star Trek format, and I've given earlier webinars on this, so you can go watch those webinars. And it will now run a program, DT scale average, and we're looking at the output of that. And the main thing here now is it gives a table 1. And it does also compute R measured, which is different from R merge, and it shows the reduced chi-square and a few other things, and so on. It also gives me the proper redundancy and the proper number of total reflections. And this is a convenient way to just plug this into your papers and so on. If I look at this, by the way, this shows the chi-squareds and everything that we saw in the other program. In HKL3000 and in ScalePack, they're actually identical. And it writes out a file which you can use in other steps. So that's SCA, that is SCA to Dirac, which does all of this for you. And I find it rather useful in that regard. So back to my PowerPoint presentation. One of the things that I wanted to also point out, this is how we get R measured. So if reviewers are asking, how do you have R measured, and you're using HKL3000, I would use this program. If you're looking to figure out what the I over sigma I is, I want to point that out here, is that there's a difference between I over sigma I, average. Notice where I have these brackets indicating average, and the average I over sigma I. So the ScalePack output shows this value. So if I look at this, the I over sigma I for some sample data that I've given here is about 20, but the average I over the average sigma I is much higher. And some people say, well, why does ScalePack always give me a higher I over sigma? Well, it's using a different definition of I over sigma than other programs. So the SCA to Dirac overcomes these different definitions and lets you stay with that. That is that. The table 1 we showed, this is for completeness, showing you what the reduced chi-squared is. It's basically what the observed spread in the data sigma squared, observed sigma squared is divided by the expected sigma squared. If you look at this in the blue highlight here, this is an adjusted sigma, and when we were adjusting the error model, we were taking the sigmas from integration and, for example, adding a 2.6% error to the intensity in quadrature by squaring that, and also multiplying the sigmas that came from Denso by another scale factor to try to make that plot flat, to have the reduced chi-squared close to 1. This number ends up here underneath this. If you look at this, this is a sample standard deviation, and I've highlighted in pink or magenta how this number corresponds to the rest of this equation. So basically we have this sigma squared coming from the spread of our observations relative to the average of those observations. And we have this sigma coming from Poisson counting statistics adjusted for the gain of the detector and a few other things. And if you take the magenta divided by the cyan or blue, if these are close to each other, they should be equal to 1. And this is the math for you, and in many places this has never been explained, so I want to show that to you here. We already talked about that. You get your table 1 out of the end of this, so you want reasonable multiplicity. You need to have good completeness. You need your reduced chi-squared close to 1, but you don't have to be, I personally don't think you don't have to go wild with making it perfectly 1. And I discussed that I over sigma I has different definitions in different programs. So if we go back to this guy, this is where we finish scaling here under this tab. This is our stuff, and I went to the structure tab. But what happened is the program warned me that I had not filled out the information on the project tab. So I'm going to edit the project, and it's lysozyme. And the thing that I need to know here for HKL3000, that it's a SAD-MAD, and it needs to know something about the sequence. So I'm going to load in the sequence. I have a bunch of amino acid sequence files in a separate directory. This is my lysozyme sequence. And I'm going to say I want to use sulfur SAD. So I've clicked here on sulfurs. There's 10 sulfurs, and then I'm done with that. And I'm ready to do the structure. The other thing you will note here is that if I was editing this project, I could click here on define, a periodic table comes up, and I could pick any of the atoms that I'm interested in as the anomalous scatterer. There is also a periodic table for the anomalous scattering wizard, and I think you guys have seen things like this. So if I click on sulfur, here's the F double prime and the F prime, and at copper K alpha wavelength, the green line is the F double prime, and it's about 0.6 electrons in here, so relatively weak for this. If you look at some of the other things, for example, selenium is used at beamlines a lot. At the peak, it's about 3.8 electrons, but at copper K alpha, selenium is at about 1.1. So this is a nice way of figuring out if you have, well, you have to use this to tell the program what you're working on. So I'm actually doing sulfur. I'm done with that. I can go to structure. And now this starts the structure tab. And inside the structure tab, there are several sub-tabs here that are familiar to people who have already solved structures. You must find the anomalous substructure. You must use phasing based on that, including some solvent flattening to break the phase ambiguity, and then you can auto trace or build the model and rebuild it in something in a graphics display program and then do refinement. And we'll come back to this in a second here. So this is the structure tab that I just explained. We'll do data analysis where we're looking at the signal to noise ratio versus resolution, and this is the delta F divided by sigma of F. And if you have a high signal to noise, the authors of HKL3000 have kindly put a gray area here where you want your signal to noise to be higher than this gray area, and a few things to check the completeness and so on. And we'll look at that in a moment. I want to say this now. The user interface for this is actually quite easy to click buttons and get stuff going. But they're writing scripts and building scripts and running some underlying programs. They use the CCP4 suite, which is, of course, written by many people. This is the reference for that. I want to make that clear. I just talked about the data analysis tab to see if the signal is high enough. It's set up to use ShellXD by George Sheldrick and his colleagues to find the anomalous substructure. We'll use that in 3 cases. The phasing is done a number of ways. Today we'll use ML-FAIR from Zbyszek-Banovsky and the solvent flattening program DM from Kevin Kaltan, and I'll show you how you can use others. Then once you have the phases, you'll have a map and you'll do auto building. We'll use ARP-Warp today from out of Victor Lamson's group with Tassos Parakis, Serge Cohen, and Garrett Langen. And then, of course, ARP-Warp makes use of RefMac from Gareb Murshidov and his colleagues, and so on. So the main thing here is you've got to find the anomalous substructure. In the old days, you know, with 1 or 2 heavy atoms in there, you would do isomorphous difference Pattersons or anomalous difference Pattersons, and some of that is done here. And I think it pays for young people in the field and old people too, why not, to go and read these papers. And this is a typo, it's Acticrist. And the references therein. This is a great program. And what we'll do here is we'll find sites for the lysozyme here. So I've popped out of my PowerPoint, and I'll click on data analysis. The output.sca file is here for that lysozyme that we just did. And here's the anomalous signal to noise. Beyond about 4 angstroms resolution, we've gone below the suggested value of an easy solution by the authors of this program. You can also do check twinning at this point, and this is running, you can see in the background here, it appears to be running truncate from the CCP4 package and so on. And you can look at the cumulative intensity distributions. And for those of you who have already solved structures, all of these plots should be familiar with you. When you go to find sites now, you can search the web like ShellXD manual, and you can get some tips. And I know that a number of our webinars have addressed this. What I'm going to say here is that if I look here, there's some nice things that are easy to do in the interface. It tells me the number of residues, the anomalous atom type, the number of anomalous atoms, the wavelength, and so on. It also estimates the solvent content, which will be used for solvent flattening. If you go to the advanced mode, you could, for example, tell it that it had disulfides, and that will turn out to be important in one of our examples. In this case, I have higher resolution data, and I'm looking for 10 sulfurs, so I'll just click on the button, Find Sites, and it converts the data for input to ShellX and runs ShellXD. And so what you'll have here is output, and this is reformatting the output coming out of the ShellX, the log file, or the output file, and it's doing its algorithm, which is partly direct methods, partly real space, moving back and forth here. And the blue dots, well, let's stay with the blue dots are the correlation coefficient of all the data versus the correlation coefficient for the weak data. And the red dots are the correlation coefficient versus the Patterson figure of merit. And generally what I'm looking for is a cluster of random guys down here that are not solutions, and then something will pop out that separates itself with a higher correlation coefficient for both all the data and the weak data. The other thing to look for here is that the average occupancy of the sites is high, relatively high, especially for something that you know is covalently bound, such as the sulfur in the cysteines here. If I had needed to go more cycles, I should have clicked here on infinite number of cycles. So it stopped when it thought it found a good solution here. That's ShellX for this. If I go to Sites View, which is a nice little tool here, these are all the runs. It did 30 runs, and if I click on Best, and it will sort them. And so cycle 26 is probably one of the best ones here. And these are showing the sites in the unit cell. The diameter of these blue circles is related to the occupancy. Here are the sites it found. If I click on Graph, what you can see here is that the site with the, let's say, the highest occupancy is scaled to an occupancy of 1, and the rest of them trail off like this. And often for something that is covalently in there, you'll see a drop in the occupancy between covalent stuff and maybe noise peaks or lower occupied peaks. So for this particular lysozyme crystal, I know there's 10 sulfurs in it, and I know, but you don't know, that there's no chlorides in here. If there had been chlorides or other halides, you might have seen partially occupied sites trailing off here. So I click Delete, and this is the way of easily editing sites here. You can get rid of these sites, and the thing changed here, and what helps confirm that this is probably the correct solution is these two atoms are close together, these two atoms are close together, these two are close, and these two are close, and they all look, you know, I can't tell the distance, but my hypothesis is that this distance is about 2 angstrom, which is what a disulfide is. And these guys are probably methionines. So if I click on phase, I almost always set the phasing resolution limit at first to, whoops, the resolution of the data, 1.6 angstrom. And because of the kind of Patterson methods used, you have to check the hands of the anomalous substructure. If you have the right or the correct hand, the connectivity will be higher for that hand than the inverse hand. And in this case, the original hand in red is higher than the blue, which is the inverse hand. So the program will not switch to do phasing with the inverse hand, and I can just click on phase. So what happens here, there's a little bit of ShellX running, then they will run ML-Fair and do the solvent flattening. So back to the PowerPoint for a second here. This is that data. This is a solution. We found it with a reasonably high correlation coefficient for all the data and the weak data. This is the plots of the various sites that it found, and I showed you how to edit the sites to get rid of some extra stuff. We are now doing phasing, and since we're using ML-Fair, I wanted to show the reference, which comes from the proceedings of the CCP4 study weekend from 1991. There's a little booklet called Isomorphous Replacement and Anomalous Scattering, and this is the place where Zbyszek Opganowski published his ML-Fair program. In addition to that, we'll follow that with solvent flattening with the program DM from Kevin Kaltan, and he published in Darsbury Laboratory publication, which was essentially a CCP4 newsletter from 1994. I clicked on the phase button. I showed you about checking the hand, and some of the plots that come out, the main thing that I'm looking at, did the figure of merit after solvent flattening look pretty good? And what happens in the processing here, it does look pretty good. The figure of merit is 0.82, and the program, HKL3000, automatically brings up COOT, which, can you see this? Because this is now an interactive display.
Yes.
Okay,
I
great.
see it.
And what they've done here is they've shown the anomalous difference Fourier in red. And if I kind of pop around and look at these sites up close, I have done this a lot of times. So whether you can tell or not, I'm telling you that that's a methionine, okay, with the sulfur here and then the methyl group off of that. If I go to this guy, that's a disulfide, and I think that's pretty obvious what's going on there. The rest of the map is pretty decent. This I'm going to guess this guy over here, and this is without fitting anything. This kind of looks like a tryptophan, and so on. So what's happened here is that the phasing has happened, and we're able to jump to the build stage. And in the build stage, you can pick, well, just a moment. In the phasing stage, you can, in the advanced tab, if you want to use something like Parrot to do the solvent flattening, I think you can do that. Yes, sorry, I clicked away, but here's Parrot. I just use DM because I've been using that a lot, and I know it's going to work for this data. In the build step, we're going to build with ARP-Warp. Basically, just click on Build Model. So while I'm building the model, I will jump back to the PowerPoint presentation. So we've done phasing, saw a good figure of merit, away we go. And this is a good reference for ARP-Warp. It's one of the more recent references found in Nature Protocols. And you should read this. It has some good tips for you. On the other hand, I have to say, HKL3000, just clicking the button, allows you to test many hypotheses pretty quickly. What will happen with the build with ARP-Warp is you'll see whether the amino acid sequence is docked or not, and it'll give you some information with that. And you've already seen that if the way it does the visualization is with Paul Emsley's COOT program, and this is a reference for COOT. Okay, and you get your result there. So over here, let's review what I've done. I've set up a project with the amino acid sequence. I found my images and data, and I processed them in the usual way with HKL. And I've shown you how I set the box size, how I set the spot size. And I also mentioned how to adjust the profile fitting radius and the sigma cutoff to not have weak data thrown out. I skipped strategy because we're not collecting the data. The data is already pre-collected. During integration, I showed you how to check to see that things didn't go wacko. And then in scaling, I said turn on absorption correction, set anomalous, small slippage, of course, do your space group hypothesis. And then I adjusted the error scale factor and the error model to get the reduced chi-squareds close to 1 for the blue line here, okay? Assuming that I plus and I minus do not match, that Frito's law doesn't hold true. That's gave me my data. I also jumped out to show you how SCA to DTREC works to give you R measured and I over sigma I. In the structure tab, we looked at the signal to noise. At the start, we ran ShellXD. In this case, I had high resolution data, so I knew I could find the sulfur separately, and I looked for all those sites. We're looking for a cluster of non-solutions versus a solution or a group of solutions that are relatively well separated from that. The sites view, we edited the sites by looking at this graph here, and for example, if I click on this and do use sites, it'll reload the graph. I talked about a drop here where the occupancy drops off given the difference between covalent stuff and perhaps non-covalent stuff. I ran phasing. I had to check the hand. I picked the hand that had the highest connectivity and some decent contrast here. And then in build, I just clicked the button. Frankly, that's all I did. And so what's happened here is in the first build cycle, it docked in 62 out of the 129 residues. The second build cycle, it's cooking along here. It's probably going to, well, it's a demo, so I know it's going to work, and so on. And then we'll get a map that we'll take a look at here in a moment. If I click on display model and map, it will bring up COOT here to look at it. So I'm going to close this guy off because the next COOT that comes up will have the model fit in it here. While this is fitting, let's jump to a couple of more examples. I have here. This is an example of, if I go to this project, this is glucose isomerase that was collected at Cold Spring Harbor Laboratory. And it has 388 or so residues. I collected 3 scans of about 180 degrees each. I ran them through the scaling, the integrations here, and the scaling, and so on. So as an example for scaling, here's the 3 scans. I deleted some bad images. The redundancy of this particular data is on I+ and I-. It looks to be between 6- and 4-fold, or overall, maybe overall about 6-fold. We'll look, because I have the things in a slide. Then I went to the structure tab and the data analysis. Check this out. The anomalous signal to noise here falls off below the into the gray area, so there's almost no signal here according to this, and the signal to noise is roughly about 1 going through here. In terms of finding sites, it's a little bit different here. The glucose isomerase has a couple of manganese or calciums in it, depends on how it was crystallized and so on. Here's a case where you have to know this, that it doesn't show anything with the correlation coefficient below 10. All of these are very likely to be solutions, and you wouldn't know this, and you might say, oh, these are all bad, random, I should give up. If I look at the sites view and sort these on the best one here, the correlation coefficient is only 19, and so on here. Here's the sites. There's 1 big one, and I have 3 small ones. I decided not to edit that. I went to phasing, and I found that the inverse hand was better. And then I went to build, and I built this with ARP-warp. And after the first cycle, it docked 329 out of 388 residues. And then in the end here, what do I have here? 368. If I look at this model, with COOT, this is the model that comes out of the glucose isomerase with almost no signal here. So I'm still building in the lysozyme, but this is a build I did just before this talk. Actually, it finished building in the middle of my talk, or at the beginning of my talk, about 10:06 this morning, my time. So here's the COOT display of the refined structure, and I have that map off, but I need to scroll on this map here. And so I think you can see here that there's a proline here. Here are the metals that it found. Here, there's a couple of them. The fit is phenomenal here. Okay, if we look through the various amino acids, this is a home lab data set collected to high resolution, so it's a pretty good diffractor. There are some issues that will have to be fixed by hand, I guess. Here's an example of a methionine where it put the methyl group in the wrong place, but these things are easy to fix. Generally what I do is I'm too lazy to fit that too well, and I'll have to do better than that. But try to get these things in there and so on. So let's see, let me put the this is the COOT popping up from the lysozyme that was fit. I'm going to reject that, and we'll go look at the lysozyme rather than dwell on the spectacular glucose isomerase map. I'm going to exit from that. So this is the auto chain tracing from the lysozyme. What you can see here is, once again, I don't think it fit the methionine right, but that's easily fixed. I'm going to turn off the original map, and I'm going to scroll the map out of ARP warp here. And so what you see here, I hope you can see this, is methionine 105, but I like to show it because it has these tryptophan, and I think that's a tyrosine right there around it. So once again, a spectacular map solved by sulfur SAD phasing. And I won't dwell on this either. So that's that. So I have 3 windows open here of HKL. So basically, this guy fit the whole structure in about 8 minutes. And you would have to go to the Refine tab now and run RefMac after rebuilding. You can check the geometry, do validation, and so on. So the example I just did was a lysozyme, 129 residues with 10 sulfurs. I showed glucose isomerase, which is 388 residues with a couple of metals in it, and I have also a thaumatin. This is the output of the table 1 from the SCA to DTREC followed by DT scale average. And the thing here is that average redundancy was about 6.5. We've done it with less than this and with shorter data collection times, but this is a data set I just collected in November, so I have it lying around. It was 87 minutes exposure time with on an imaging plate system, collected at 1 degree per image. The thaumatin data, which it doesn't look like I have time to show, but it's 90 degrees of data, and the average redundancy was 6, so it's about 3-fold on I+, 3-fold on I-, and it's good data, and collected, and it's spine splice data, so 0.3 degrees on an imaging plate system. It has 17 sulfurs. The glucose isomerase was collected at Cold Spring Harbor lab during the Cold Spring Harbor methods in X-ray methods in structural biology, and it's on a Rigaku, another Rigaku rotating anode, the MM007HF with a Saturn CCD detector. These were the data collection statistics on it. The average redundancy was a little bit higher for this weaker data. The conclusions are from this data, and I didn't show the thaumatin, I didn't have time, but you can have redundancy as low as 3 to 4 on I+ and on I-. Even low delta F over sigma F can work. The glucose isomerase kind of shows that. Some of the rules of thumb, like you must have correlation coefficient above 30 or whatever, it's not quite true. George Sheldrick's ShellXD is amazing at finding the anomalous substructure. I didn't have a chance to show that any phase improvement is helpful in auto tracing. So sometimes you can't build the whole thing, but you just click it again, and using the phases you have from the previous partial auto tracing, and instead of doing 3 builds, you might end up at 6 or so, and everything works. So I want to just say, try many things. HKL3000, the graphical user interface, makes it as easy as a mouse click. I want to thank my colleagues again, and I want to thank you guys for watching. So I think I'm ready to take a few questions.
Okay, great. That's fabulous. Thanks, Jim. So if you have a question, then go ahead and type those in. I have a couple of questions already, but I wanted to go back to one thing, question from me that I don't know if some of you caught, but I'm wondering about the SCA to DTREC. So do you need a special version of D-Star Trek for that? Which versions have that in there if they wanted to use it?
The most recent version of SCA to DTREC has not been distributed yet. So the last distributed version of D-Star Trek was in July, and there is a version of SCA to DTREC in that version that people can use. This more recent version, if I type SCA to DTREC here, if my screen is still being shown, right?
It is, yes.
So in this particular version, I made it even easier to use, because if you have the file name nomerge_output.ska, it looks for that. And in the old version, you had to put in the unit cell and space group. In the new version, it tries to find that unit cell and space group from another file in the directory. So this will be in the next version of Star Trek, and if you need this or want to use it, send me email, and I'll see what I can do to get it to you.
Okay, great. So then just to press forward with a question from Teresa. She was hoping you could give some tips for data collected at 2.8 angstrom for using something like this for structure solution.
The thing is, you're going to end up taking the data that you have. And most of these things were high resolution, but if you have selenium and so on, you're going to still be able to do some of this work. Okay, so with the anomalous wizard, for example, you can, let me see where I want to go with this. You can still plug in seleniums and so on. I think at 2.8 angstrom resolution, it's going to be a little bit more difficult, but what can happen here in the structure tab, you will see stuff where, if for example with selenium, that this red line will be up higher. It may be that you can do a halide swish, say iodine or bromide or even chlorides. But if you're trying to do sulfur SAD with sort of barely 2.8 angstrom resolution data, it's going to be a little bit tougher. For one thing, if you have disulfides, you're going to have to do something. I'm looking now at thaumatin, which has disulfides. You're going to have to go in the fine sites. You don't have enough resolution to separate the disulfides, so you have to go to the advanced tab, and you have to tell it how many disulfides you have. And in this case, I didn't go through this example, but this solution does not come up if I don't tell it that I have disulfides. The other thing you can do is you can limit your high resolution limit here. I know my colleagues, they look at this graph and they say, oh, the high resolution limit, I would set it to where the red line crosses below. This is about 1.3 here, and they would use that. What I would say is with this interface, you can try many things. So if I had 2.8, I would try that. Then I would try 3.0, then I might try 3.2, and so on, and just to see what happens. You can let this run a lot longer. I know in the CCP4 interface, I think it's 200 tries or 300 tries, and so on. But you got to have reasonably good data to do sulfur SAD. Okay, so I can't. You know, if you have 2.8, it might be tougher. Although yeah, I'll stop there.
Yep. Do you have a recommendation for data resolution for trying sulfur SAD?
I would try it with anything. Okay.
Yeah.
The main thing here is that it's so easy to put in a halide. I don't see why you don't try that as well.
Sure.
Okay. Tom Edwards from Emerald Biosys gave a nice webinar on that, and you should watch that and decide what to do with that. It's really pretty good. Okay.
Yeah, had good success with that, and that one is recorded and it's on the website. So I agree, you should try that as well. So Mario has a question. He wants to know for the glucose isomerase example, how many of the Shell XD solutions were correct? Did you look at that, and did you have to do any guesswork in picking the right solution?
Let's look. So here I am looking at this. If I look here, there's only like 33 tries. There's a big difference between finding like one site, even if it's weak, and finding a bunch of weak sites, okay, or even a bunch of sites that are commonly like the same occupancy, like in sulfur SAD with lots of sulfurs. And in this case, probably most of these sites are all legitimate because the metal sticks out by itself. If we look at this, we only ran 28. Well, sorry, let's look. We ran 33 cycles here. And I basically stopped it early because I knew that the solution was the right one. These other guys, 3 and 4, these guys are actually turn out to be sulfurs. If I go and look at the map out of phasing, display this map, This won't have any of the amino acids fit in yet at this stage, but we can flip through the 4 or 5 things and we can look at the anomalous difference Fourier that it calculated. The thing with this is a lot of people give up too soon, okay? I think if I do that, that's the first one. There's the second one, which it's a methionine. Third one is a methionine. Fourth one looks like a metal. No, it's a metal. And those are the 4. But you can see out of the corner of your eye, it didn't get this. This is likely to be a chloride ion. And I think in this particular structure, there are a number of sulfurs that it didn't pick up. So what you might do to help phasing is, and I didn't do this here, is to go back and complete the anomalous substructure by looking at anomalous difference Fouriers and plugging it in. And I know that Randy Reed has his phasor package now through the CCP4 interface, goes back and looks at the log likelihood gradient map and will look for secondary, more sites than ShellX found, fill them in and do phasing that way. I also believe, that the Phoenix will do the same thing. Phoenix, in my opinion, the Phoenix His is not quite the same as ShellXD. And what you might have to do with your toolkit is use ShellXD with Phoenix or with Phasor in the CCP4 interface, or HKL3000. To go back to here, you asked, how many of these were right? Probably all of these are close enough to be solutions, and there's like 5 of them there out of 33. So more than 20% were right. That's a lot different than this guy, which is the Thalmatin. I did stop it early, but there was it's one site here. So you just try it. And what I would recommend that people do, and some people don't have time to do this, is to grow a Thalmatin or a lysozyme crystal and get some experience that you can apply to your own protein.
So we have another question from Dilip, and he's collected at BM14. Maybe that's APS.
ESRF maybe.
ESRF maybe. Okay.
Yeah.
2.9 angstrom data set. And he tried to solve the structures with AutoSolve, but he's saying he had a problem with data quality. So then he started shooting for redundancy, and he collected 360 frames of peak and remote data. And so I think what he's basically asking is, so if you have a problem with data quality, will redundancy help you if initial methods fail? What do you recommend?
Well, that's an interesting question. So if you're looking for sulfurs and seleniums, the longer you collect data, especially at some of these hot beamlines, is that you will now have radiation damage, and the sulfurs and stuff can move around. That may be an opportunity to use iodine, because I don't think you're going to get radiation damage with iodines. They're not going to move around very much. You might change their occupancy and so on. So rather than it's a trade-off. If you have more redundancy, you may have more radiation damage, and it may be harder to solve the structures, okay? And we've seen some things where the seleniums are disordered, and in fact, which map is this? This is the glucose isomerase map. There is a disordered methionine in this map here. This is the Thalmatin map, and if I bring it up, you can see this and so on. So, it's still an open question. Some people would say collect fast, lots of redundancy. In our hands, collect reasonably good data from the get-go, and you don't need the redundancy. And I'm sure that both methods work fine, and you may wish to try both ways. Okay, so if you collect fast, though, and with high redundancy, more things can go wrong, I personally think. I'd rather get the data that I know can do the phasing as quick as I can.
And speaking to that, too, I know of examples in our lab where we've cut back some of the data
Yeah.
and long data collections have been more successful than using all the data where you might have damage. So there's a question from ARCA, and the question is, can we handle severely twinned data having significant crystal slippage? And this is in their case, they've collected a cobalt SAD data, and it sounds like it's going to be challenging.
Yeah. So So what I'm going to do is I'm going to jump to the project, and I'm going to go to the anomalous wizard and do the cobalt story here. In theory, cobalt would be great at copper K alpha. It has as many electrons as a selenomethionine at a beamline. You know, you got to do a good experiment. So you have to ask yourself is why was your crystal slipping? All right, and fix that. Okay. Certainly HKL does a good job of tracking the flow of the crystal, but and so does D-Star Trek and the other packages. But it's just one more thing that goes into it. You know, it adds systematic error to your data, and it's probably better to collect good data from the get-go. So it was not only the crystal slippage, Angela. What was the first thing?
Severely twinned. So I'm not sure if that means cracked or really twinned.
Yeah. So if it was cracked, I know that we collected a crystal here from a local group, and it was cracked, and we didn't see it, and we solved the structure. But then the next day we put on a non-cracked crystal, and the results were much, much, much better. So, you know, if you have what you have, I can say you can work at it, but it's probably best to spend your time on getting better crystals and becoming better at mounting them, and so they don't slip and so on. So I do know this, like crystal slippage sometimes is not really the crystal slipping. It's some of these cryopins, if they don't warm the bases up to room temperature, they will be moving quite a bit. And at these fast beam lines, sometimes people don't give it a chance to come to thermal equilibrium, and the difference in the thermal expansion coefficients of all the metals and everything cause these things to move around in the beam a little bit, and that can degrade the signal and increase the signal to noise.
Definitely. We have a question from Robert, and so I'm going to interpret. He's asking, why do we frequently see red density at the anomalous sites? Is that due to radiation damage? And I'm guessing he's talking about a difference map. Or I'm not sure if he's talking about this, and that's just a coloring scheme.
Yeah, so this is just a coloring, and so the resonance scattering of the electrons in here give rise to a signal that we're using to do the phasing. There's a phase shift because of this, and we measure that phase shift by looking at I plus and I minus, and then use that to get the phases for the rest of the molecule combined with solvent flattening. If atoms move, you'll get a difference Fourier as things move around, and this is actually the results of the thaumatin that I wanted to just touch on for a second. And what you see here, here's a peanut shape. Shell XD did not find this other sulfur. It just found the one sulfur there. Here, for this disulfide, it found both sulfurs. Here's a case of a methionine that's disordered, actually. You can see that well, I happen to know from looking at the refined maps that the side chain goes up this way and also goes up this way. It looks like it's at least 60% occupied on this side and some on this side. But Shell XD just put one atom right here, and it's probably not in the right place. Here's another disulfide where it only found one in the center. You could probably get better phases if you can get better phases if you complete this properly and put in the anomalous substructure. But even with these atoms not particularly well determined, you can already see the map behind the scenes here is really quite spectacular. It's a high resolution map, though. I'm not sure what's going on here. So basically I would say I would not be afraid to go and always try to fit the map, even if the map looks crummy. I mean, auto trace it with these new powerful methods. They do a great job. As for, you know, maybe radiation damage as things shift around, cut your data back and see if it helps you.
So ARCA actually commented on her twinning. It's non-mirrohedral twinning, so
So it's like a cracked crystal,
Yeah.
I guess. Yeah. Yeah, one of the things you can do with difficult data to process is if you post to the CCP4 news group, for example, a lot of people will jump in and help you. Certainly at Rigaku, people can send us their images and we will look at them. It's better if you're a customer of Rigaku and certainly using our equipment, but I know that we look at many beamline images for people. Life is too short to not bring in an expert when you're struggling.
Yeah, definitely. Okay. With that, then I just wanted to thank you again, Jim, for your talk today, and it was really, really great. I also want to thank everyone for attending today, and if you're certainly welcome to share the recording and the link. It should go up in a couple of days, and we hope to see you again next time. If you have any questions following the webinar, please feel free to email those to Jim or myself. I'll make sure they get to the appropriate person. And I'd also like to thank all of the authors of the programs that Jim mentioned today. Thanks, Jim. Thanks, everyone.
Yeah, thanks. My pleasure. Bye, everybody.